Hello everyone. Hope you are all having a good evening. So I just wanted to go over the solutions to the Unit 3 test review that is on Pearson here. Just to kind of give an overview for what you can expect to see on the test as we kind of go for it as we take a look here. So starting off, looking at number one, a couple of definitions. We're being asked to figure out the definition that goes alongside the complete collection of all measurements or data collected versus a sub-collection, so like a little smaller subgroup of the overall collection. This is, of course, going to be describing our population as the larger kind of one population as the large collection of all data. The sample, which is a subgroup, is maybe slightly imprecise, but we're going to go with it, a subgroup of the population. Now, important definitions that go along these, when we are talking about the actual measurements that we are collecting from a population. So this is a descriptive measurement that is just saying what is going on with the population. Think, for instance, of the mean of the population. When we have measured the population, we're not guessing as to what the mean is. We know for a fact, after we have done the measurement, after we have done the calculation, that this is the true mean. When we are discussing that, we are talking about a population parameter versus when we are taking a look at a sample, we are looking at a sample statistic, which is just to say it's basically a parameter, but it is there's a little bit of guesswork, right? We don't know for a fact that the statistic is right on the nose, perfectly describing what is going on with the population as a whole, but this is like our guess to what is going on with the population. And this is the actual population value. So for instance, we could talk about the population parameter of mean, which was mu. So this was the parameter. This is the actual true mean versus x bar, which is the statistic for our guess at the parameter based on a sample. Same with sigma and s, certainly extend that definition there as well. Right. So looking at number two, we are being asked to find the mean, median, mode, mid-range, and mean, median, mode, and mid-range for the data that we are given. So looking at number two, we're going to go ahead and go to our calculator here. We're going to go to stat, edit, and we're just going to enter all this stuff into a list. I'm going to clear L1 here. Going into L1, so this is 219. This is 295, 200, 205, 281, the most riveting part of a statistics class, watching the teacher enter the data into their calculator. 8, 292, 295, 295, 278, 249 again. So then I am going to do a couple of things here. The first thing that we're being asked to find is going to just be something that we can pull up with stat. So if we go stat and then over to calc, do one variable statistics, and that is going to pull up pretty much all the information that we are going to need. So for instance, being asked to find the mean in this case is that 256.2. So that is that X bar that we see there. So X bar to 256.2. Important to note, because these are 11 players that are being randomly selected, this is a sample statistic, which isn't relevant here, but certainly if I asked you to figure out the standard deviation, that is information that would be highly, highly relevant. What do you mean? This is spelled correctly. Yeah. Sure. Doesn't like my hand. That's okay. All right, for the median, scrolling down there, looking at the median, we see that the median is 263.5. And we can give the mid-range as well, which is just going to be the average of the max and the min, which in this case is going to be 200 plus 295. Dividing that by 2, we get 247.5 for our mid-range. Now for our mode, my recommendation would be to take a look at the list, but in order, just to see everything kind of arranged here. So I'm going to go to sort A, just to sort everything. And you have to tell it what list we want to sort. We want to sort L1 here. And so in this case, you'd have to generally on your calculator, you'd have to go back in and actually look at it. But taking a look at the list that we see here, we can see that the only instance of a repeated value is 295. Cool. And so our mode here would be the value 2. Looks like there's a follow-up part there. And then it asks how generalizable. This is interesting. How generalizable are these results? So would this be representative of all players in that league? An interesting thing here is that because this is a sample pulled from the championship team, we would expect the values here, which are representing what are we being told? The weights in pounds. We would probably expect these to be pretty exceptional. We might expect these to be like more extreme than what we might see on other teams. Right? Just because we're dealing with an exceptional team, we probably would not be able to generalize those results. All right, 3 is asking the same thing. It just has you do the mean and median for 2 different data sets. An interesting thing that you could do for that is you could enter one of the data sets into L1 and then one into L2, and then do 2 variable statistics. So if you go to calc 2 variable stats and hit enter there. Okay, in this case, it says that they have to be equal length, so my actual values don't quite work for it. But that would give you the mean and the median for both. You could also just run 2 one variable statistic analyses, and that would also be perfectly acceptable. Nothing wrong with that. Nothing different there. Okay, cool. So let's take a look at number 4 here. This is going to be a weighted average. Using a frequency distribution. Okay, so in this case, we are asked to compute the average number of degrees based on the frequencies that we see. Now, the main issue that we have with our kind of like frequency distribution that we run into very, very quickly is when we look at our weighted averages here, the weight of 1 times x1, which I have kind of gravitated towards thinking of this as like a fraction of some kind of total, and this as the value that that fraction represents. When we sum up all of our weights and all of our values, we normally like have an actual like value of like x to put to this. The problem that we run into very quickly with our frequency distribution is we're looking at our first weight being attached to 40 to 44, right? This is not one single value that we can attach a weight to, but that's okay. What we need from here is a representative value, which is very simply going to be the midpoint. We've used this as a representative value in the past. So the midpoint that we would see here is 42. Now, what I notice that for all of my temperatures, for all of my data, I have 2 plus 7 plus 11. I have 28 data points here. And so for 2 of those 28 data points, I see a temperature on average in the middle of a 42. So again, this is just representing the 40 to 44 category. All right, and so we're just going to go through and sum these up. Between 45 and 49, I see 7 of my 28 data points, which we will represent with a 47. I see 11 of my 28 represented by 52. 6 of my 28 be represented by a 57. And then 2 of my 28 represented with a 62. And then you would just plug this into your calculator and get some kind of value, right? Which we could do. It would not be too difficult. I'd expect this to be actually pretty close to 52. Mostly just because I'm noticing that this distribution is relatively symmetric. It would maybe be a little bit, it might be like 51 point something, but I would expect this to be very, very close to 52. All right. All right, another weighted average problem for number 5. You could do a very similar thing again. Think about like what fraction for the weights, what fraction of the total number of points his grade represents, but very, very similar here. Measure of tendency for number 6 that is the greatest frequency. We call that mode, not too bad. Cool. Let's take a look at number 7. This one's a fairly quick one. In this case, we were being asked to figure out the variance given that the standard deviation, in particular the sample standard deviation with 10 subjects is equal to 11.2063. That whole like 10 subjects thing, none of that is important. We are being asked to find the variance. Note that the standard deviation is just equal to the square root of the variance. And so the variance is just equal to the standard deviation squared. Okay, that's not too bad. S squared is going to be like what, 125, 11.2063 squared is going to be, yeah, 125 point, told to round to 4 decimal places, so 581. Cool. Just variance, taking that standard deviation, which is normally what we're going to be working with, square. Okay. In this case, we're being asked to figure out the symbols or list the symbols for number 8. I've already done so here. So notice in this case, we were working with a sample. Whenever we're working with a sample, we're going to be using our English letters. If we were instead working with the population, the standard deviation will be referred to as sigma, and the variance would be sigma squared. So this is standard deviation. This is our variance. It doesn't matter as much with mean. The whole like difference between a population statistic and a population parameter and the sample statistic. Here it is incredibly important that we get this right. Because you will notice if we go into the calculator and look at our one variable statistics, when we use S for the sample statistic, we get 37.5 from this particular data set. And when we use sigma, we get 35.6. Now, I don't remember exactly why these are different. Actually, I have a good idea of why they are. I think it has to do with the fact that, again, when we know that everything that we're looking at is, in fact, this sigma, we have a lot of confidence that we are looking at one particular standard deviation, whereas if it's just a sample, we allow for a little bit more wiggle room. You'll notice that this S is a little bit larger than that sigma. I think that's consistent across the board. So the S just allows for a little bit more wiggle room than what we see with sigma. They're different. They're different values. If you pick the wrong measure of standard deviation, you're just going to get the answer wrong. Please do not do this. S is sample, sigma is population parameter. Right? Greek goes to population parameter, mu, sigma, what have you, that is referring to population. Okay. Quick thing about number 9. So this is again looking at like standard deviation for a sample. So we would use S. Range, if we're talking about the range of our data, that's very, very simply just going to be the max minus the min. A kind of subnote is that we are looking at the interquartile range, which is the range between the quartiles. Then the IQR, right? Then this is just Q3 minus Q1, just like how this is max minus min. This is Q3 minus Q1 for that IQR, which this isn't asking about, but I just wanted to connect those two vocab words. They're the same thing. Number 10, very much the same question. That's not too bad. Okay, let's take a look at number 11. This one's not horrible either. So in this case, we're being asked to figure out using our bell curve. So first thing to note, 1, is that we are working with a bell curve or a normal distribution. And we're being asked to estimate the amount of kind of data that we see under the curve based on our empirical rule. Now, what I gave for our empirical rule was 68, 96, and 99.7. And I like that empirical rule. And so I will stubbornly adhere to it. But the one that you are probably more likely to see in the wild is 68, 95, and 99.7. But again, this 95 isn't actually 95. It's closer to 97. So we were asked to figure out the approximate percentage of people with this platelet counts, of women with this platelet counts, within 3 standard deviations of the mean. So for a normal curve, if we are within 3 standard deviations of the mean, then this is going to be that 99.7% of our data. So this is within 3 sigma. And then we are asked to figure out the number that are within 2 standard deviations. Now, it isn't explicitly said that what we are looking at is within 2 standard deviations, but we certainly could figure that out. So for instance, we are told to figure out the number of women between 125.6 and 391.2. We think of our mean as being, in this case, 258.4, with our standard deviation being equal to 66.4. Then going out 2 standard deviations, you'll notice by the time we get to plus 2 sigma, go ahead and plug this into your calculator, adding 2 sigma to that particular mean, we are at that 391.2, and minus 2 sigma will take us to that 125. So we are within 2 standard deviations. So we have 95% of our data. The only difference that we have really between number 11 part B and number 12 is that we don't know whether or not this is a bell curve. No knowledge of shape. And so as a result, we are going to need to default to using Chebyshev's theorem in order to figure out what's going on. Right. So in this case, we're trying to figure out, not knowing anything about the standard not knowing anything about kind of what's going on here, other than the fact that the mu is equal to 98.24, and that the standard deviation is 0.59. We are being asked to figure out what is going on within 2 standard deviations. Okay. So Chebyshev says, as long as I give you a number that is greater than 1, I can give you an estimate for the percentage of our data that's going to fall within this particular range by doing 1 minus 1 over that standard deviation squared, which in this case tells us that we should expect to see at least 75% of our data within those 2 standard deviations. Now again, what does it mean to be within 2 standard deviations? Well, that is taking our mean, 98.24, and adding it with this 2 times sigma, so 0.59, to get this upper bound, and taking our 98.24 and subtracting it by this 2 sigma in order to get our lower bound. Plugging these into our calculators, we see a lower bound of 97.06 and an upper bound of 99.42. So we would expect to see at least 75% of our data between these 2 values. All right, empirical rule, sure, for number 13, that's not bad. Okay, how do we then kind of deal with, this is going to be like z-score stuff. So what does it mean to see a z-score of, say, this is number 14, what does it mean to see a z-score of 4.10? Remember that this is talking about the number of standard deviations that we are away from the mean. In this case, because we are positive, we are going to be above the mean. And so this is saying that we are 4.1 sigmas away, or above in particular, above right? So in this case, asking us to rank z-scores and say which one that we would prefer for our next test in statistics. The larger the z-score, the higher above the mean you are. So you'd probably want a z-score of 2.00, which would put you in, interestingly enough, the 95th percentile, or close to the 95th, more like 6th percentile, right? But relatively close. Too bad. Okay, cool. Let's take a look at the number 16. Number 16 is going to be kind of an application of this, not an application, but actually computing this z-score. In this case, we are told that the lowest pulse that we see, so the value that we see, the minimum value is 36 beats per minute for heartbeat, whereas the mean, in this case, it's from a sample. So the mean from the sample x bar is equal to 79 beats per minute, and the standard deviation of that sample, 27.8 beats. We are being asked to find the z-score, which again we can think of as the number of standard deviation. Just because we're talking about a sample doesn't actually change anything. So again, we're going to find how different is our value from the mean, and then we're going to convert that into a number of standard deviations. So 36 minus 79 tells us that we are 43 below the mean, so negative 43, which we can interpret as 43 below the mean. Notice 43, if we're looking at number of standard deviations, this is going to be between 1 and 2 standard deviations. So just as like a rough estimate, when we do this calculation, we'd expect to see somewhere between 1 and 2. The way we actually do that conversion, dividing this by our standard deviation of 27.8 to get, in fact, that we have a z-score of negative 1.55, which we can interpret as saying we are 1.55 standard deviations below the sample. Okay, so we consider, so part D is kind of getting at a little bit of an interpretation piece. So pulse rates that have z-scores between -2 and 2 are not particularly surprising. We would expect, so this is kind of thinking back to what we did in 1.3, we would expect that to happen about 96% of the time. 96% of z-scores should fall between -2 and 2. And so if we're saying that, you know, this is going to happen more frequently, this falls within that 96 kind of percentage expected value, then this is not particularly surprising. And not surprising kind of translates to not statistically significant. Statistically significant. Statistically. So we're going to get more into like statistical significance using these z-scores later. This is ultimately why we use a z-score, is to determine if a result is particularly. All right, so same deal with number 17. In this case, what we find is a z-score of like 5, which is very, very unlikely to get by chance, which means that we should be very, very surprised when something comes up. Okay, So in this case, we are told, looking at number 18 here, we're being asked to figure out at what point we see statistical significance. So again, this is we're getting a little bit ahead of ourselves, but that is okay. These problems aren't too bad. We want to think again, we want to be between -2 standard deviations and 2 standard deviations from the mean. In order to be like our expected range of values. So anything less than this and anything more than this is going to be surprising. In this case, we are told that our mean in the recent year, okay, whether that's a test statistic or whatnot, we'll use it as population. We'll say that the population mean here was equal to 19.6 and that the standard deviation was equal to 4.7. Within 2 standard deviations, our lower bound that we would expect, the lowest test score that we would expect to see and not be particularly surprised at, is 19.6 minus 2 times the standard deviation of 4.7 gives us a value of 10.2. And on the flip side, the highest value that we would expect to see, again, kind of within that 2 standard deviations mark, is 19.6 plus 2 times 4.7. This works itself out to be 29.0 on the dot. And so anything between 10.2 and 29.0, we would be not very surprised. And again, interpretation pieces, this should happen about 95% of the time. And so when we see something that does not fall within this range, we say, wow, the likelihood of that happening just by random chance is like 5% or less. If our alpha value is 5%, now we start to see, okay, here's where the tie-in is with all the hypothesis testing that we were doing. Technically, what we have constructed here is called a confidence interval. Which we will come back to in chapter 6. So we'll get to it. But for now, just kind of note that that is what we have arrived at, is this idea of if I go 2 standard to the deviations to the left, I get at this value. And if I go 2 standard deviations to the right, I get this value. This question is also equivalent to just answering the question, what is the value that we see when z is equal to 2 and -2? So that's the z for that. That's the z. But not too bad. Okay, so we've done 19. That's just finding more z-scores. That's not too bad. 5 table or 5 number summary. Remember for our calculator, so this is for number 20. When we go into our calculator, the 5 number summary that we see is min, Q1, median, Q3, max. So it's these last 5 values that we have for our one variable statistics. Otherwise, you just plug them in, pull up the table, see what those 5 values are. People did pretty well with that on what we have. Box and whisker plots, not too bad. And data is converted into a standardized score. Okay, so standardized using the number of standard deviations. So that's talking about a z-score. Data is considered significantly lower, significantly high. Sure. Technically speaking, again, this is why I did not like the 95% rule as part of this. It's negative 1.96 and positive 1.96. But again, we're not going to get too persnickety about this. We'll kind of get to it later. If we are less than the mean, then we have a negative z-score. Sure, that's not too bad. Which of the following is not part of the 5 number summary? It's min, Q1, median, Q3 max. The only one not mentioned there is the mean. It's its own thing. All right. Find the variance for the given data. Okay, sure. So that's not too horrible. All we would do to find variance, so this is for number 25. Skipping ahead a little bit, had a few vocab ones here, but number 25. So we could figure out the mean, do this by hand. Sure, it's not too horrible to do by hand. In this case, trying to look here for something that would tell me whether this is a population or a population or a sample. And I don't see anything right away that is cluing me in one way or another, right? Maybe these 6 appliance stores are literally the only 6 appliance stores that have this model. Maybe not, I don't know. Let's enter in the data and we'll see what this ends up working out to be. And then we'll make our determination from there. Which I don't love doing, but I think the wording here makes it kind of not super clear whether what we are working with is a population or a sample, which again is very important for standard deviation and variance because it's going to determine which of those values we actually use. So 174. Okay, we're going to stat, calc, variable statistics. Cool. So I'm either looking at, okay, these are pretty vastly different. So if it's a sample, then S is 213 point, what does that say? 15. And if it's a population, then my sigma is 190.6.64. So again, relatively close. Again, notice that the statistic is a little bit larger than the sigma, than the parameter. Just there's a little bit more wiggle room, a little bit more guesswork when it's just a sample. So squaring these values. Okay, so that one's too big. That one's larger than any of my other options. So clearly this is referring to a population. And we'll try and be as exact as we can. You don't need to be this exact, but just because the two answers that it gives are so similar, and we are squaring this. And I get, okay, apparently I didn't need to be that exact at all, but $36,354, and this will have a say and 3 cents. That doesn't even line up. Huh. I enter the data wrong. So 663, 273, 410, 622. It didn't take my last data entry. That'll do it. I was gonna say, like, that seems off. Okay, so it's okay. So this is going to be using probably the population, but let's try. So 175 squared. Okay. So actually, this is important of which one we're working with. 191.93. 297 squared. Again, it's not super explicit, so I'm not really happy that it has this as kind of like this multiple choice. Because it's not very clear, maybe we would say like there are more appliance stores than 6 appliance stores, and so we're calling a sample of those appliance stores to get that sample statistic. That's probably reasonable. That's probably what they're going for. So in this case, we use the sample statistic, which we found to be 191.933. So S to 191.933, S squared being equal to $36,838.3. Technically, it's dollars squared because we square it, but that's not the we're not worrying too much about that. Okay, find the range. Already looked at that. Find the mean. Z-score. Okay, that's not bad. Notice in this case, Z-score of 4.5 is outside of the plus or minus 2, so very unusual there. Definitely very unusual. Another Z-score for 28. That's not too bad. Okay, I want to take a look at 29. So we've done a lot of taking information and converting it into a Z-score. Let's take that Z-score, which in this case is equal to, so this is 29, equal to negative 1.5, and we are going to convert it, given the fact that the temperature 98.2 degrees Fahrenheit, sigma is equal to 0.62 degrees Fahrenheit. So we are looking at this. This means that we are 1.5 sigmas below the mean. Okay, so we can take our mean, 98.2. We are subtracting 1.5 sigmas, literally 1.5 times 0.62, to get ourselves a value of, in this case, 97.27 degrees. So literally taking this definition, 1.5 sigmas, 1.5 standard deviations below the mean, and writing it as an equation that we can answer. Not too bad. Okay, and 30 is a repeat question. We already had that. All right, I hope this was helpful. I will have this posted alongside the rest of the other, I think there were a couple of other Unit 3 lectures that hadn't been posted just yet. So all of that will be on the YouTube link. If you have any questions, please do not hesitate to reach out. I'd be more than happy to take a look at anything that you guys might have. But regardless, best of luck in all of your studying endeavors, and I will see you all tomorrow. Have a good night.